Today we're going to learn Hess's law and heats of formation. We've already learned the phase changes. So there's three ways to calculate heats of reaction or energy of reaction. First one, which is the MCAT, which we've been doing since last week, relates a temperature change to the mass and to the specific heat constant to calculate the energy released or absorbed by a reaction. This uses the law of conservation of energy. Then we did our specific heat capacity lab, where we did the heat lost by a reaction, or in our case, a metal, was equal to the heat gained by the water. Those are the types of heat of reaction problems you expect to see with the MCAT, which would be the phase change diagrams and the calorimetry problems. Next is the enthalpy of formation, which we'll go over a little bit. This is taking data from known sources, so looking it up in a table. We want to do a little bit of practice with looking it up in a table because it's not something that you do a lot of anymore. We do a whole lot of Googling. We don't really do a whole lot of looking stuff up. But all of this will be listed in tables in the back of your books, and it will be helpful to at least have the skill to be able to look this stuff up, at least know what you're doing in finding this type of material. Because you can't always Google everything, can you? Have you ever Googled something you knew the answer to and came up with something ridiculous So you got to be careful on what you look up on the internet. And the last is Hess's law, which we'll also learn today. So Hess's law is when you're taking known reactions and then you're using those known reactions and manipulating them using the fact that they're a state function, and combine them in such a way to calculate the enthalpy of a target reaction which is unknown. So we know lots and lots and lots of reactions. You can look up the enthalpy of reaction, but we can't possibly know all of them. So Hess's law is a good way to get unknown information from known information. So let's first start with heats of formation. This is pretty straightforward. There's tables that you can gather information from, but elements are always zero. And let's talk about this. Because when an element is in its standard state, that's how it likes to occur. That's how it likes to exist. That's the way it's going to hang around. So when you look up the enthalpy of formation of O2 gas, it's going to be zero because that's the way it likes to occur. You look up the enthalpy of formation of calcium solid, it's going to be zero. Now let's look at bromine. If you look up the enthalpy of formation of Br2 gas, it's not going to be zero. Br2 liquid is going to be zero. Iodine, if you look up I2 solid, that's the one that's going to be zero, not I2 gas. This is dependent on the number of moles. So when you're calculating a chemical reaction, you need to account for the coefficients when it comes to this way. And we also need to use this equation. This is a type of equation that you will see bouncing around, but it makes me a little bit nervous because the negatives and the positives in thermochemistry only refer to the direction of heat flow. So remember I told you in order to break bonds, you need to add energy. And when you make bonds, you get energy back. So breaking bonds is endothermic, making new bonds is exothermic. That's why the reactants get a negative sign. So it's not plus, because what we're doing is we're forming the products. So we put them down as is. The enthalpy of formation of the products is what you will look up. But the reactants, we're not forming the reactants. We're doing the opposite of forming the reactants. That's why we get a negative. So as long as you remember that when it comes to any equation, anything that's on the reactant side, those bonds are going to be broken. Therefore, it's endothermic. Anything that's on the product side, those bonds are going to be formed, so they will release energy. When you look up a list of enthalpy of formation, they're all going to be negative numbers. You will change the sign if you're not forming them, if you're breaking them. So let's look at an example. I'm just going to look it up in a chart and I'm going to list them. Notice aluminum solid, that's in its standard state. Element in its standard state is always negative. We're going to look up Fe3O4 and we're going to look up Al2O3. Those are negative numbers, meaning that when you form those compounds, energy will be released. And when I say enthalpy of formation, that's to form them from their elements in their standard state. So to form Fe3O4, you would have to make the coefficient on Fe3O4 1, and you would form it from Fe solid and O2 gas. Same thing with aluminum oxide. You would make aluminum oxide from aluminum solid and O2 gas. And then obviously iron 0 also. So let's plug these in, remembering that look at what happens because of that negative there. The reactants become positive or endothermic. So it's essentially the same thing as changing the sign. And overall, this reaction, what do you think? Endothermic or exothermic?
Exothermic.
It's exothermic. So remember that first day when we were first doing these reactions on the board? If it was exothermic, we put the energy on the product side. If it was endothermic, we put the energy on the reactant side. So exothermic reactions have negative enthalpy, or heat is one of the products. All right, let's get ready. Let's dive into Hess's law. So the change in energy or process or reaction is called a state function. That means regardless of the pathway to reach your goal, the energy to get there is constant. So that's a little bit difficult to understand because we're not used to state functions. You know, if you ask me, can I go to the main office? You could be like, okay, I'm going to go straight there and do what I'm going to do. I'm going to take a right-hand turn out here, go down those stairs. I'm at the main office. Or you could decide, oh, I'm going to go see what my buddy's doing in the class down the hall, and I'm going to go to the bathroom back there and stuff. You know you're going to spend more energy if you go the long way. But when it comes to chemical reactions, that's not the case. It's called a state function because the starting and the ending positions are the only thing that matters. Regardless of how you get there, you're going to spend the same amount of energy. For instance, if you want to vaporize a solid, you have two pathways. You can either melt it into a liquid and then take that liquid and vaporize it into a gas, or you can sublime it straight from a solid directly to a gas. Either path gets the desired result, and either path requires the same amount of heat energy. This is what Hess's law is. Let's look at what a picture of that looks like. So you see the amount of energy we have to spend for the enthalpy of fusion added to the amount of energy that we have to spend for the enthalpy of vaporization is equal to the amount of energy of enthalpy of sublimation. So during any Hess's law calculations, there's two things that you can do. You can reverse the reaction, making the reactants the products and the products the reactants. This is called flipping the equation. If you flip the equation, you simply write the reactants as the products and the products as the reactants, but you have to change the sign of the enthalpy change. You can also increase or decrease the amount by changing the coefficients. You can change the coefficients by multiplying by a factor. If you multiply one thing by that factor, you have to multiply everything in the equation, including the enthalpy, by that factor. We're going to keep our eye on that goal reaction, which is always going to be our destination. So they're going to give you, this is the reaction we're hoping to get to, and these are our known equations. Let's see what that looks like. So here's our reaction. I want to find out how much energy is exchanged by forming N2O5. I can't look it up, so I decide I'm going to use Hess's law. And here's the equations that are given to me. So what I always do is I start at the beginning. I'm going to start at the beginning and say that I need 2 N2s in the reactant side. I look down at my equations. I usually number them 1, 2, and 3. So equation number 3 has N2 in the reactant side, but the coefficient's not quite right. The coefficient's 1, and I need it to be 2. So I'm going to multiply that third equation by 2, the whole thing by 2. I'm going to skip over oxygen. Here's another helpful suggestion, is when you see something that is in more than one equation in the bottom, don't try to mess with it. Hope that it falls into place. Here's another spoiler alert for you here. In this class, because this is the way it is on the AP exam, if you are given 3 equations, you're going to use all 3 equations. So don't get confused and say, I wonder if I use this or not. You're going to use all of the equations that I give you, and you're going to use all the equations that I give you only once. So the next thing I'm going to do is find N2O5. Well, that's equation 2, N2O5. I need it to be in the product side, and I need it to have a coefficient of 2. I'm good. I'm going to use the second equation as is. That means I don't change it at all. Now I have everything in place, but I have to make sure I can cancel the things I don't need. And the things that I don't need, you can see I've got 4 NOs in the third reaction that I don't need at all. It's not my target reaction at all. So let's take equation 1 and multiply that by 2 also. Now we've used all 3 reactions only once. Let's see if we can cancel out the things we don't need. Those cancel. 4 NOs and 4 NOs. Those cancel. So now I have 2 N2s, and let's check out those oxygens. We can cancel them if they're on the opposite sides of the reaction, meaning one's a reactant and one's a product. But if they're not on the opposite side, we add them together. So the first reaction has 2 O2s, second one has 1 O2, third one has 2 O2s, so that is a total of 5. So I take equation 1, multiply it by 2, add it to equation 2 as is, take equation 3 and multiply it by 2, I add it up, and my enthalpy of formation of N2O5 is 24 kilojoules. Is that endothermic or exothermic? It's endothermic, meaning that it would be a reactant. Energy would be a reactant. Okay, so we're given 3 equations, and our target is written at the bottom this time. So let's just start at the beginning. C2H6. I find C2H6 in the first equation, but I need to multiply the first equation by 2. Then I'm skipping over oxygen because oxygen's in more than one reaction. I'm going to go to CO2. I have CO2 on the products with a coefficient of 4 in the target reaction. I find CO2 in the givens in the third reaction, but it's in the reactant side, and it only has a coefficient of 2, so I'm going to have to flip it and multiply it by 2. So I'm actually multiplying it by a negative 2. Like such. So there's where I stand right now. Now I have C2H6 in the reactant side like I want. I have 4 CO2s in the product side like I want. I just need to fix my waters and cancel out C2H4 and H2. C2H4 already cancels out, but I can see that I have to flip the second equation in order to get those to cancel. Now my H2s cancel. My C2H4s cancel. I have 6 plus 1, 7 oxygens in the reactants, along with that particular compound is called ethane. And then I have 2 plus 4, 6 waters. So I'm all good to go. Now I got to add these guys together. And here's another way to check if you're correct, because combustion of a hydrocarbon reactions are always exothermic. So if you have a CH compound that's combining with oxygen and you get CO2 and water, you always expect exothermic reaction, meaning that the enthalpy value will be negative.